patterns. A lot of what we're going to cover this chapter is patterns and dealing with patterns. Being able to do stuff. Pascal's triangle is used for a lot of things in the world, none of which I'm really going to go over right now. But it's a pattern that's all over the world, that it does different things. I'm not going to try to explain any of them to you right at the moment, just so you can see it. How would I get this number right here? How'd you know it was 1? All right. Where you guys are letting yourself get confused at is the way I look at it, and maybe you can see it this way, maybe you can't. I see these 2 blocks right here, and they touch that block, right? Yeah. Does everybody see that? Yeah. So guess what I do with those 2 blocks to get that guy? This one here only touches that one, so it's 1. These 2, you get 5 there. If I can fit it in these blocks, what's this one going to be then? 10. Okay. How about this one? How about this one? 1, 6, 15. Is that making sense? Does it make any sense? So let's look here, Caleb.
So it's like every block that touches gets added together.
The blocks, if I was drawing this out, let's say I was drawing that next row, I already got this. How many blocks do I got to cross that last row? 8 and 7. 1, 2, 3, 4, 5, 6. I had 7 blocks on that last row, right? This next block, it only touches that one, doesn't it? So it's just 1. This one touches these 2. So you add those 2 together. What were those 2? 1 and 6. So what do you get here? 7. Next block touches these 2, which is those 2, right? Which is 21. So we got 1, 7, 21. So it makes sense now, Caleb?
Yeah.
So what's going to go right there? 35. Here. 35 again. Here. Be careful.
21.
21. Here.
Okay, I see.
What goes here? Last row probably will do. 8.
28. 70. 56.
One's already in there. Could we keep going?
Yeah.
When would we have to stop? Wouldn't it? It's going to keep going forever and ever and ever. All right, so you could keep going, and that's just a pattern, and that's one of those patterns. And I'm not a scientist. That's so Caleb when I said everybody should have their books out over to page 71, right, Chloe?
Yep, 71.
Books out, page 71.
You need this?
No, we just stick it off to the side. Maybe
Throw it away?
finish a whole lot of it later or something,
You
and
throw it away?
not right this moment, but. Page 71, first thing I want you to do is look at problem 19. Chloe, was that one you had a question about? 19?
What do we do with the big size?
Yes.
Come on, I'll tell you. We'll talk about this in a little while. Problem 19, everybody's looking at problem 19. This is one of the key ideas I wanted to make sure you got from section 2.1.
I had to do it
What, me just having this up here
Yeah.
made it seem a little simpler? So you want to write an if and then statement. You want to write converse, inverse, and contrapositive. So you got to be able to do all 4 of those things. First is an if and then statement. Remember, that's also called a conditional statement. If and then statement's also called a conditional statement. with these conditional statements. It says if, and then whatever the first part is, what's that first part called again? Hypothesis. The then is the conclusion. The if part, the hypothesis, that's the part that we're taking for granted. Somebody's telling us that that's true. Alright? The then part is what we're going to make our decisions off of. So if I say, if Caleb, then something else, we know the Caleb part's true, and then we're going to make our decision about the second part, whatever it is. Alright? Whether the whole statement's true or false. On this one, it says, you do your math homework, you will do well on the test. First, let's write it as an if and then statement. So how am I going to write that as an if and then?
If you do
what?
your math homework.
If you do math homework,
And then you do all the tests.
then you will do well on test. Sorry about my cursive's not very good. Doesn't help any that the pen's messing up. What's this part called again?
Hypothesis.
Hypothesis. What's this part called?
Conclusion.
Conclusion. Remember, the hypothesis doesn't include the word if, it's just the part that's with the if. Conclusion doesn't include the word then, it's just the part that's with the word then. Looking at your notes or looking back in the book or whatever you have to do there. For the converse, what does the converse do to that original statement? Switches these two. It takes the hypothesis, moves it over to there, takes the conclusion, moves it over to here. So it switches the two. So what would the, first of all, let's go back to this one, because I forgot this part right here.
If you do well.
Is that true or false? If you do your math homework, then you will do well on the test.
False.
It could be false, but we're gonna go with true because in my experience, if you do your homework each day,
Depends on the person.
right, that might be, but I don't go for the fact that people say, oh, I'm just a bad test taker. No, we've already had that discussion, right? You're a bad test taker because you don't prepare up to the test. That means doing the homework and stuff. That's what makes somebody a bad test taker. So we'll say that that's true. What would this be if I switched them around, if I switched those two?
If you do well.
Conclusion, hypothesis.
If you do well on test, then you what?
You do your homework.
You did your homework, right? So if you do well on the test, then you did your homework. Is that true or false?
False.
That one I would say maybe could be false, because are there people in the world who can come in here and just do the test and never ever had to do the homework? Yeah. Austin, are you one of those?
Yeah.
Yeah, see, Kenneth, I sort of believe that you are, and that's why I said my little statement a few minutes ago that you're one of them that I'm probably gonna be real mad at the end of the year, because if I'm telling you this towards the end of the year, that's gonna make me mad, the fact that you could get out of this class fairly easily and just didn't. We don't want that. Don't shrug your shoulders. We don't want that. So that's probably false. Inverse. Looking back at your notes, what's the inverse do to the original statement? Negates both parts, right? So you're going to take this statement and you're not going to switch them around. You're not going to switch them around. You're just going to negate both parts. And that negate means you're going to make both of them sort of the opposite of what they did say. All right? So what's this part going to say?
If you do not use math homework.
All right, if you do not do, and I'm starting to shorten this up because I hate writing. If you do not do your homework,
Then you will not do good.
then you will not do well on test. Is that true or false?
Sure.
maybe. Again, these are subjective, so can I really, if I put this on the test and you told me the first one was false and the second one was true, can I really? Huh?
Is it more of an opinion thing?
In this case, yeah. Now, there'll be a lot of them that aren't just opinions that,
This one really depends on the person.
right. So this is more, we can't really say, hey, this is for sure true or this is for sure false. But some of the others that have math stuff in them, then we can say, yes, this is true, no, this is false, and there's no, two different ways. Contrapositive,
It switches and negates.
switches and negates. So what would the contrapositive say?
If you don't do, oh, if you don't do well,
If you,
do a lot.
now, before we go any farther, and I don't think this book does it, but I know the old book did it. Make sure, number one, I always say make sure you go back to the original statement every time when you're doing converse, inverse, contrapositive. All right? But some people don't want to go clear back to the original statement. What's the contrapositive do to the inverse?
Just switches it around.
It switches around. So once you write this inverse, could you just take those two things and switch them around, and that would be the contrapositive? And if that helps you to do it that way, then do it that way. But make sure you don't get yourself confused, whichever way you decide to do it. So if you don't do well on test, then what?
You don't do your homework.
All right, and we want to make it make English sense, right? So you didn't do the homework. Is that true or false? False. Now, something that I may have forgotten to say with this class because we ran out of time. If the original statement here that we made, the if and then statement, if that's true, about 99% of the time, guess what you know about the contrapositive?
It's true.
It's true. So if the original statement's true, a good guess is that the contrapositive is also going to be true. All right? And again, for these, this is sort of subjective, right? So we can't really say if one's true or false, or because it really doesn't fit to say for sure that it's true or false. Did you have another one of those? What was another one of those? Let's just go over it real quick. Find me one in there that had some math in it. Let's see here. Early child, homework, 23.
They didn't even do 23.
Yeah, I was trying to look for one that more had geometry stuff. So let's do 66 through 69 on there. What did they ask you to do on 66 through 69? So that's 27, 28, 29, 30. Oh, right there. Write the next two numbers. So somebody come up and do number 66 for us. Kenneth, go up there and do 66. Kenneth wrote in 911. Everybody agree with that? Somebody go up there and do 67 for us. All right, Caleb, take your calculator and go up there and do it.
Oh, kind of, see what it is.
All right.
Alright. Can it go through clutch?
No, it's not.
Oh, there you go. Yeah, you're a liar.
Somebody be doing the others. So when I call on you, you're ready to go up there.
Wait, I gotta write. Do it.
Number 60 is hard.
Does everybody agree with that? 56 and 67? What was the pattern there? Adding 11 each time. Now here's where you guys get yourselves into trouble. Because when you start seeing patterns, and every geometry book I've ever taught out of, and every algebra book I've ever taught out of, does this to you all the time. They'll do the first like 3 patterns, and they'll be adding 2, adding 11, adding 15. And then all of a sudden they'll switch it and make it some different pattern, where you're not just adding. And then guess what all of you guys are looking for? What you should have been adding. And that, it doesn't work. How about 68? Nobody wants to try?
I don't know how like you get that. What it's going on by.
How about if we do this, and then Bree's gonna come up and do it. Are you ready, Bree? Watch, because I'm gonna show you where most of you get confused. That first number right there is confusing the heck out of all of you, right? Because all the rest of them are fractions. That first one's not. How can we make that first one a fraction? Put a 1 underneath it. You put a 1 underneath there, now all of a sudden can you start to see a pattern? Yeah, I got it. You don't need it. Bree's gonna help us out, right, Bree? Hop up there and do it for us, Bree. What's the next number? Grab your calculator, use it.
Teachers, excuse the interruption, but can we have Lucas Boggs to the office, please?
Somebody be ready on 69. Be ready to do that one. You wanna do 69? Come on, Bree, you make it harder than it is. Put too much thought into it. Bree, what's going on top?
You got a times by 2, right?
And what's going on the bottom?
Times by 3.
Okay. Write your next fraction. Choose your calculator. So use it. Make it easy, don't make it harder than it has to be. Probably gonna need it on the next one, right? The comma. Do the same thing. Caleb, you see where she got that?
No.
So she's not gonna find it when she gets this other one, I think.
I think I know 69, I'm not sure.
Oh yeah, I think so.
So how'd she get it?
So at the top, like times 2, and the bottom times 3.
So this time, instead of adding, what were we doing? Multiplying. So they switched it up on you to try to confuse you. Did it work? Yeah. Right? And especially it worked because this first number right here, the 2, they didn't write it as a fraction. But always know that, can I go back and write it as a fraction so it looks like the rest of them if I want it to be that way? Yeah, it might make it easier on you. All right, Hunter. 69. Everybody agree with those two? How, so explain it to me, because I don't understand that. Goes up by 3, then by what? 5, then
7, 9, 11.
Really?
Yeah.
What, because I thought maybe it did some pattern like this. I thought maybe it multiplied this by 3, so 3 times the number, and then added 1. Something like that. That won't work?
No, because it'd be 12, maybe 13. Or 4.
Oh, it would be? Is this the only pattern?
No.
No, and I'm trying to think right now, cause I know there's like other pattern that fits that, and I can't think of it. My 3 up by 5. Oh, yeah, now I know what it is. How about this pattern? How about, I'm just looking at this. What do you notice about each of those numbers if you're looking at them separately? They're both what, or they're all what kind of numbers?
Not a perfect square.
Perfect squares. Could we maybe use that?
Oh, yeah, the perfect squares are right there.
Now, is that gonna give us the same thing that Hunter got? Yeah. Might that have been a little easier than trying to add 3, then 5, then 7? Say, oh yeah, these are all perfect squares, so the next one's gotta be 5 times 5, which is 25. Other questions off the page, look through them. Other problems you wanna see worked off of there? Ask now. I know Bree's probably got a bunch of questions.
40.
Is that one of these?
Yeah, she's flipped.
So let's do 39, then we'll do 40, all right? On these truth tables, because I put and I just put these on here, so I forgot they were up here. On these truth tables. Now we're back on 39. So you might want to turn the page back. On these truth tables, they look like this. And I know we didn't get all the way through them in some of my classes. Don't make them harder than they are, and we're not going to actually do a whole lot with them throughout the year. But if we're trying to decide whether this statement right here is true or false, well, that statement right now doesn't make any sense whatsoever. Kenneth, read that statement to me. Somebody help him out with the little tilde. Not.
P, something, Q.
Now this.
Arrow.
The arrow here. This arrow means implies. You'll hear me say implies a lot. So, not P implies Q. Okay, not P implies Q. We could have, that arrow, we could have just easily have, put something in here like not P tells us Q, so whatever. Alright? This goes to this. So the first thing I'm going to put right here is I'm going to put P. Even though there's no P anywhere in here. We got not P, but we don't have P. Then the next column, I'm going to put not P. What am I going to put in the third one? Q. Then in our fourth one here, we're going to put the whole statement. Not P implies Q. So we're trying to decide whether these are true or false. So Lexi, what can you tell me about P? Is it true or false? It's true. All right. Now we could go across and do it, but Lexi told us P was true. Caleb doesn't believe her, do you, Caleb? No, because you think P is what? False. All right. So we have P is true. Well, that doesn't tell us anything about Q over here. If P is true, then Chloe, Q could be what?
False.
Could be false. It could also be true. Well, we don't have any place to put that. So what else do I need to do over here?
True, false.
Put another true and another false. So P is true, Q could be false. If P is true, Q could be true. Just like on a true and false test where you match them up, all the possible ways that you could get the answers, right? Kayla, you never done that on a true and false test, just went down through and guessed, have you?
You never done this?
Huh? On a true and false test.
Huh?
On a true and false test? You've never done a true and
Oh,
false
yeah.
test?
I think like a table.
So we're looking at that. Now we said P was false, so what would Q, or what could Q be? True. Now before I go through all this and do all this, I'm going to do this, because you guys are making this a whole lot harder than it has to be by not staying in some kind of order. This is the way I make up this table, so I make sure I don't miss anything. For P, I know that I need 4 separate things for P, so I say, okay, it could be true, true, false, false. We do that every time. All right? And then we go over to Q and we match them up. Well, if P is true, Q could also be true. If P is true, Q could be false. What's going to go here? True, false. Do you see how we got every possible outcome now? We got a true, true, we got a true, false, we got a false, true, we got a false, false. So that way, if you do it this way every time, you're going to make sure you get them all. So 2 trues, 2 falses, and then true, false, true, false. So what do we know about not P? If P is true, then not P has to be what, Evan?
False.
False. Lexi, if P is true, not P has to be what?
False.
Caleb, give me these last 2 here. Now, all we're going to look at, we're looking at this right here, so we want to look at these 2 things. We got a false and a true. Not P implies Q. Well, if this is false and this is true, what's that tell us about the whole statement? False? Everybody agree with that? If they're both false, what's that tell us about the whole statement? They're both true? False? So what percent of the time is that statement, even though we don't have a clue what that statement says, what percent of the time is it going to be a true statement? 25%, 1 out of every 4. Alright? What was that, number 39? Let's make sure, flip in the back of your books where the answers are. And see, real quick. The bad thing is I don't always give you the, it's wrong. It's wrong?
Yeah.
You don't know yet?
Yeah, definitely wrong.
It is?
Yeah. It should be all true, 1 false.
All true and 1 false? Is that the way it is? How do you know?
You also do, I just copied that one, I didn't know what I was doing.
So you copied it out of the back of the book?
Yeah, if they're not, I didn't know what I was doing.
So it says,
I'm being honest.
so it says what?
It's true, true, false. True, 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 false. So it goes, the topper goes true, true, false, true.
True?
True, false, true.
What did they switch these around?
Yeah.
Yeah.
They got them switched around?
Well, see, we still have all the right answers.
So these are all right, right? These,
But this should be
Yeah.
true.
these are all right, but this one here is the one we got wrong, right?
Yeah, it should be true, true, false. True, 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 false.
So the only one that,
The only one that was right was the bottom one.
right, tell me what they got here.
You don't have 40.
No, tell me what they got.
P,
P,
Q,
Q goes next,
P.
not P,
Yeah.
and then not P. P implies Q. Alright. See now, with this book, it's a little different. Books I've taught out of in the past, number 1, you wouldn't put that arrow in there. Because that arrow doesn't really mean anything. Alright, that's where, remember last time we talked about the and symbol, or the or symbol? That's what should be in there. So that we know, hey, are we saying both these have to be true for the whole thing to be true? Or only one or the other has to be true? Alright, so for P, what did they put?
Down.
Yeah.
True, true, false, false.
So they did it that way, same as we did it, right? True, true, false, false. 2 trues, 2 falses. For Q, you have to match them up. So we say a true, then a false, then a true, then a false. Alright? Then we look back at P. What's, if P is true, then what's that tell us about not P?
False.
It's got to be false for both those. And see, and that's why I'd rather put that over there, because then you can look right next to them and not get as confused maybe. If P is false, then what do we know about not P?
Both true.
They got to both be true. Now, if we're over here if, see, I was going on the fact that I think that arrow should mean and. If that arrow means or, then only one part has to be true for the whole thing to be true. If it's and, both parts have to be true. So you guys, and that's on your notes, that's where we were talking about conjunctions and disjunctions. Conjunction is what you tell your parents all the time. You say, Mom, can I have $10? And she says, what do you need $10 for? Well, I need to go buy me some school supplies and I need to buy me some snacks and stuff. And they say that sort of fading off, right? And you go and you buy a 10-cent pencil and $9.90 worth of crap, right? Now, if you said and there, when you told her that, did you lie to her?
You did get both, technically.
Yeah, but, you know.
You kind of fade off saying it.
If you say and, both parts have to be true, and if you didn't hardly spend anything on the, yeah, I guess that's true, you did spend something, so I'd have to say you went to the grocery and just spent it on junk and didn't buy any school supplies.
Yeah.
Alright, now if you said or in there, would you have lied to her then?
No.
No. So this, and I'm not sure, anybody see anything in the book there? Flip back a couple pages, let's look at their truth tables.
Yeah,
So they're using the arrows, let's see if they tell us what the arrow means. Use the truth table, converse, inverse, also they're doing it for all of them, but do they really ever say what the arrow stands for?
It is interesting to know if this means that, if arrow means it's gonna go.
Yeah, that's what they want you to know. This means this goes to that. But how do we decide here if it's true or false unless we know that both of them have to be true or only one or the other have to be true? So what they're saying with that arrow apparently is that the arrow is like an or, and just one part has to be true for the whole thing to be true. So if we look here, is one of those two parts true? So what's that tell us about the whole thing?
True.
True. If we look here, is one of those two parts true?
Yeah,
So that tells us the whole thing's true. If we look here,
it's true.
true.
And then false. But to me, no.
Yeah, that's right.
Yeah.
I got something messed up somewhere. What did I mess up?
No, you have true.
That's
false,
right.
True, false, true,
False,
false. Now you have two falses.
Oh, I'm looking at the wrong ones. I should be looking at these together, shouldn't I? This one here is gonna be false, because both parts are false.
No.
No, it's
And
true.
then that's true.
No, the bottom one's false.
Bottom one's false,
As it,
and the rest are true.
Well, we wrote it different. Because look here, because these are the two things that we're looking at. The Q and the not P, right? We got a true and a false there. I was looking at the P, and we don't want P as part of it. So those two together gives us a true. Those two together, where they're both false, give us a what? False.
That's not what it says.
Really?
Book says it's true.
And it's
one
got,
says true, true.
And it's got it written just like that.
Just like that?
Yeah.
that doesn't make any sense whatsoever. then.
Yeah.
So we're not gonna do a whole lot with those truth tables.
I like it.
Huh?
I like it.
Well, at least you're honest.
Yeah, they're not hard. I mean, even if we have this, and you look down through here and there's 16 boxes there,
You can figure it out.
could you get 14 out of the 16 boxes right? Yeah, that might help your grade a little bit. Other questions? Other questions off the homework?
You think that's it?
Yeah. Don't even roll your eyes, because I wrote your notes for you last time. No other questions? Caleb, you just ready to move along?
Yeah.
Alright, go ahead and start copying this down. Reasoning. We're going to talk about reasoning. We're going to move extremely quickly. The title is reasoning. And what we're gonna do is be able to use inductive and deductive reasoning. Anybody have any idea what the difference between inductive and deductive reasoning are?
Deductive is not like.
Give, take away. Deduct. Take.
Deductive is put in, deductive is take down.
You're putting in a reasoning
Insert.
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 Good guesses, but. Yeah, I lost it. Yeah.
I just love reasoning.
Do what?
Love reasoning.
You did?
Yeah.
Why did you spell it wrong? So what we're gonna cover, using inductive reasoning, using deductive reasoning. And the next slide's gonna show you what inductive reasoning is. Inductive reasoning is what we were using last time. When you were finding those patterns, you were using inductive reasoning. Deductive reasoning is something a little different. Deductive reasoning is when you use rules, laws, ideas, postulates, theorems, properties. Use something like that to only did you get it. Just for reasoning twice that confused me. That's right, reasoning twice. Oh, it goes. You make things hard. You can understand that? 5 minutes from now, you're gonna be able to understand it? Okay, good. Deductive reasoning is when you use some kind of rule or something to come up with an idea or come up with a conclusion. All right, write these down. And conjecture. Conjecture. Conjecture is a statement based on observations. So it's a statement that we base on observations, based on something that we've seen. So anytime you're making any kind of statement, that's a conjecture. So in the book, when they say, come up with a conjecture from the following, that means they want you to come up with some kind of statement based on what they told you. Now, if they ask you to come up with a conjecture, and the problem says something about 2 + 2 = 4, 3 + 2 = 5, and Lexi comes up with the conjecture that cows are black and white,
That's not true. Not all cows.
am I going to be able to mark that conjecture wrong?
Yeah. No.
Not really. Would I mark it wrong? Yes, I would. But, because it didn't have anything to do with the problem, right? But when you're coming up with a conjecture, it's just a statement. That statement could be true, it could be false, could be anything based on whatever you're given. Inductive reasoning. Inductive reasoning is reasoning that uses patterns to make a conjecture. So when Caleb came up here, Caleb, if you had to come up here and look at this pattern and you had to write the next 2 numbers in the sequence, what would you probably write?
4 or 5.
4 or 5?
4.
4 then 5?
Yeah. Stupid thing.
So Caleb says to write 4 and 5. Now the bad thing with that is, and the bad thing with using inductive reasoning a lot of times, I didn't see that. my next two numbers would have been 5, then 8. Who's right, me or Caleb?
We really
Caleb.
Both are right. And the reason, when you're just given 3 things,
All you can do
is that enough to make a pattern out of it? Not for sure, right? What pattern did Caleb use?
+1 +1
Plus 1, plus 1. What pattern did I use?
+2 +3.
Sorta. I took these 2 and did what with them to get this next one? Add them together. Then I took these 2 and got 5. Then I took those 2 and got 8. What would the next number be? 13, so on, so on. Is that fine? Were they both right? Yeah. Now, do we know for sure which one's right? Not really. So inductive reasoning doesn't always work real well. If Caleb's walking through the door and he's tardy every day, and I tell him, hey, don't be tardy today, and I know that he's gonna walk in tardy, does that mean he's gonna be tardy? Can I just assume next time, so I'm setting up at my desk, I can put a tardy in the grade book for next class also? No, even though I've seen him be tardy maybe 4 times in a row, does that mean it's gonna continue to be that pattern? No. If you had, then I'd give you the detention already. So inductive reasoning, not always the best way to do things. Because you're looking at patterns. A bus driver, the example I use all the time. If you drive a bus and you know that Joey doesn't get on the bus on Tuesday mornings because his mommy brings him to school every day on Tuesday mornings because she works early or something. And the bus driver's going down the road, that's Tuesday morning, does that mean the bus driver can just fly by Joey's house? No, because there's gonna be that one Tuesday where mom didn't have to work early and he's gonna get on the bus. So if the bus driver used inductive reasoning there and said, oh, I've seen this pattern every Tuesday, so I'm just gonna fly by Joey's house, no reason to stop, then it's not gonna work. So that's inductive reasoning. Making a conjecture, coming up with something based on patterns. All right, numbers such as 3, 4, and 5 are called consecutive integers. Make a conjecture about the sum of any 3 consecutive integers, then test it. Give me something.
3 4 5.
3, 4, 5, we got, that's 12, right? So 3, 4, 5, 3, 4, 5 added up to 12, 6, 7, 8. What'd that add up to? 21. 0, 1, 2. I'm gonna put it down here so that 0, 1, 2. What'd that add up to? 3, 4. Then what? 9, 10, 11. What'd that add up to? 30. You don't know, grab your calculator, but don't say anything. Then what?
11, 12, 13,
11, 12, 13.
36.
Oh.
Oh, 12, 13. Okay, never mind. What?
11, 12, 13.
No, it's 12, 13.
That's all right, we can do that one. You said that adds up 36. We can do the next one with 12, would you say 12, 13, 14? 39, does it matter that they overlap like that? No, there's still some pattern there. Nobody's seeing a pattern yet?
I am
What?
+9.
Plus 9 each time?
On the first 4. On the first 3.
So when we went in some kind of order, you could add 9 each time?
Yeah.
How about if no matter what numbers we're picking, that 11, 12, 13, because it doesn't fit into the plus 9, but it's still 3 consecutive integers, right? You don't see a pattern using all that? How about if I did this? Same thing there.
Times by 3 each time.
So what conjecture could we make? If we pick 3 consecutive integers, we know that their sum is going to be 3 times the second number, the middle number. So let's pick and see if it works. Give me 3 other consecutive integers.
14, 15, 16.
14, 15, 16. Somebody add those up real quick. 3 times 15 is what, 45? See if 14, 15, 16 add up to be 45. Is that a conjecture we could make about that pattern using inductive reasoning? Yeah, so anytime you see 3 consecutive integers, you could say, hey, I know that they're gonna add up to whatever that middle number is times 3. That's the kind of stuff you need to be able to do with. Some of the 3 numbers will be 3 times the middle number, or some of the 3 numbers. All right, write this down, a counterexample. Counterexample, very, very important counterexample. Counterexample is a specific case for which a conjecture is false. A specific case. You got to be specific. So, if you tried to give me a counterexample and you said desk, that probably wouldn't work. If you said this desk, then that's specific. So if I made a conjecture that everybody's name in my Brown 3 class has fewer than their first name and last name, everybody's name has fewer than 10 letters total. Is that true or false? False. Now, when something's false, you need to be able to give a counterexample. So what could you give me as a counterexample? What's your name? What's your name, Caleb? Count up the letters. How many in your first name? 5. Now count up the number in your second name. 8. So 13 total. Is that less than 10? No. So what could it, so for my statement, for my conjecture that I made, what counterexample could you give me? You could write out Caleb Clayman, because that would be a counterexample. That's the specific counterexample. If I said, let's see, all, so it's still 12. If I said all students in Geometry Brown 3 class are 15 years old. Is that not true? Now, you got to give me a counterexample, so what would you do? So you would say, Kenneth Rusk is 16 years old. That would be a counterexample. And it's specific, all right? It can't be somebody in the room's 15 or 16.
Could you write that right
15, yeah, you could. But you'd have to, again, it's got to, you can't just write their birthday, you'd have to still give their name because you want a specific example. All right, deductive reasoning. This is what we're going to use most of the year in geometry. Deductive reasoning uses facts, definitions, rules, properties, etc., to form a logical argument or to come up with a logical conjecture. Inductive reasoning uses patterns. Deductive reasoning actually uses the rules. When you were doing this last year in algebra, 3x plus 2 equaled 8, and you did this, 3x equals 6, and then you divide it by 3, and you got x equals 2, you were using deductive reasoning. You were using the rules. What rule did I use right here when I moved this 2 to the other side? Anybody remember that? You're going to learn it next time for sure. If not, use the subtraction property of equality. Remember that property said that you could subtract 2 on both sides and still be the same thing, right?
Yep.
And then what rule did we use here at the end? Division property of equality. Alright, so all that, when you were solving all those equations, you were using deductive reasoning. Got to know counterexamples. You gotta be able to do counterexamples. You can't just say, oh, this is false. Gotta be able to give me a reason why. Oh, this is false because,
So you can't just say this is false because it's stupid, like you have to give an actual reason.
yes, you have to give a reason. Alright, law of detachment, write this down. Law of detachment. This right, yeah, let me erase that. Let's see, because I got to make sure that I tell you the best way to write this down. You see this? That's true. So I'm telling you that that original statement is true. Then I'm telling you this is true. Does that make sense, sorta? It's gonna make sense. I mean, does it make sense? You see how I split the P off and I'm telling you the P all by itself is true. So, and that's what this is telling you over here. The original statement is true, and the hypothesis alone is true. What does detachment mean? As you're writing this down, what are you doing to it?
You're taking it away from the group.
Taking it apart. And that's all you're doing here. So you got something like this. P tells us Q, or P implies Q. And I'm telling you that this whole statement is true. All right, Caleb, that whole thing's true. And then I do this. P all alone is true. So when P's all by itself, it's true. Guess what you can decide about Q then? It's true all by itself. All right, that's what this says. So law of detachment just says if the original statement's true, and the first part of it's true all by itself, then the second part has to be true all by itself. Chloe, does that make sense then?
Well, if the whole statement is true, then wouldn't both parts be true anyways?
Not necessarily. So if I gave you this statement, I said if Tom then Joe, and I told you that statement was true. All right? And then I tell you Tom all by himself is true. Then what do we know for sure? Joe's true all by himself. All right? And the reason it doesn't work, I'm trying to think of a sentence here. If a dog then has, no deformed dogs here, I'm not going to listen to any of that, so don't say nothing stupid, then has 4 legs. Alright? So, if we look at that statement, if a dog, then it has 4 legs. And I tell you that Kira is a dog. Then what do you know about it?
At least
Has 4 legs. Alright? So, just because I'm telling you this whole thing's true, does that second part have to be true? No. It's based on the fact that we know that you have a dog. Because I could say, Kira is a chicken. And then can we say, oh, then it has 4 legs? No. Because Kira wasn't the dog part. The dog part wasn't true all by itself. That makes sense? Right. So on this, if 2 segments have the same length, then they are congruent. AB equals QR. So what's that tell us about them? They're the same length, right? They have the same length. Well, if they have the same length, then what can we say about those 2 segments? Then they are congruent. So so the statement we could make mathematically is we could say segment AB is congruent to segment QR. Remember to use your symbols. What's this symbol mean again? Congruent. That should have been written down here. That's the conclusion we can make from that. So the first thing that we had to, if we know this whole statement is true, then we had to know that we had two segments that had the same length all by itself, then we could say
There.
they had to be congruent. Alright, so if I would have said something like angle A is congruent to angle B in that second statement, could we have said then that they, well, that's not a good thing, because we already said that they were congruent. Yeah, I can't think of anything to put in there right now to make it so it wouldn't work. Alright, law of syllogism. Law of syllogism, write this down. This one's a little tougher. Law of syllogism. I shouldn't say that. It's probably actually easier.
Law of syllogism.
Law of syllogism. What happened to it? It disappeared, didn't it? Law of syllogism. You're going to start off, you're going to be given two statements. And if they're telling us that those two statements are true, then we're going to make a decision or come up with a conclusion off of that. What's the hypothesis in this first one? P. What's the conclusion? What's the hypothesis in this one?
Q.
And then what's the conclusion? See anything there?
Nope.
Let's go back. Hypothesis. Conclusion. Hypothesis. See anything? Alright, in algebra you probably did something like this. And I know we're going to cover it next time. A equals B and B equals C, then what conclusion could you draw? A equals C. And that's sort of the same thing here. If P tells us Q, so P goes to Q, and then Q goes to R, guess what shorter route we could take there? Then P goes to R. That would be our conclusion. Then P is going to tell us R. And we know that that's going to be a true statement. So if these two are true, then we can come up with this conclusion on our own and say it has to be true. So Caleb's going to be able to do this next one for us. So Caleb, I tell you, if horse, then bell. If bell, then airplane. We know that these are both true.
The airplane is what?
Because I'm telling you, right? Those are both true. Well, what could we say down here then? If what?
Then, if airplane.
If horse.
Airplane.
If horse,
Horse and airplane.
then airplane. Does that make sense? So you're saying, horse tells us this, that tells us this, and that tells us that, then we could say that this right here has to tell us that. Just sort of take that shortcut to it. Alright, get out a clean sheet of paper. Clean sheet of paper.
I'm ready to
Do it quickly, because we're going to go over these problems, and I'm going to move very quickly. If you don't get them written down, as I'm going over them, you're out of luck. Number 3. I know Caleb doesn't, it's the weekend, he doesn't want me to do any of his homework. Because he wants to have to do it all on his own, right? Yeah. He doesn't want me to do it. Number 3. Everybody look at number 3.
Nope.
Describe the pattern and write or draw the next two numbers, letters, or figures. So let's just write the next two numbers or whatever. What they do on number 3? So went what? Positive to negative, then back to a positive, right?
Negative 6.
So if we described that, if we described it, how about if we said times by what? What would you times by to go back and forth positive and negative? -1, and then go up 1. That'd be a description. What's the next one? -6, then what? +7 or -7? Number 4. 0, 2, 6, 12, 20. Anybody see a pattern there?
0, 6, what?
0, 2, 6. Where's your book at? I ain't reading it back to you. Get your book open. Goofball.
So far away.
You guys are telling me I should just go sit down. You don't want me to do this for you, do they, Kate? So it went up by 2, then went up by 4, then went up by 6.
It went up by 8.
So what's the next one gonna be?
10.
30? 42? So how could we explain that?
It went up by
Goes up by 2 to
up
already added.
by extra 2 each time, maybe? Could we
Yeah.
say something like that? It goes up by an extra 2 each time? Number 5, ZYXWV.
-1.
-1.
Minus a letter.
So letters are going what?
Down.
Backwards?
Yeah.
So what would the next one be? U? T? Everybody agree with that?
Yeah.
Austin's doing his alphabet so he can figure out if.
Can't do it backwards.
So Austin, make sure that you don't ever go out and drink and drive because that's some of the things that they make you do, right?
I can do it, I'm really good.
Number 6. Number 6, a little tougher on this. JFMAM. Anybody have any idea on that?
No.
No.
I don't have any idea on this one, really, but think it through. What do you think it might be?
Maybe yeah.
A random letter.
JFMAN.
I think next is gonna be like JF, ma'am. So it's gonna be me and JF.
Probably not.
Probably not.
FJ.
Look at it. Think about it.
FJ. Because JF and AM would be AM, FJ.
Nobody's got it yet? Ah, you're supposed to tell them. You're supposed to make yourself look smart and.
Dang, what's J's afterwards too?
JJ.
Oh, yeah, it's JJ.
JJ? Is that right? What's this?
January, February, March, April, May, June.
April, May, June, July?
Oh.
Number 7. Number 7. Got triangle, then a 4-sided figure, then a 5-sided figure. What do you think's gonna come next? 6-sided. What is a 6-sided figure? Hexagon. What's a 7-sided figure? Heptagon. 8-sided figure? Octagon. Sort of upset me that they're on the test. Some people didn't know 8-sided was octagon. Number 8. What's gonna happen next? What'd you start off with? One block, right? Then what happened? Put a block under it and one on each side, right?
What's that?
Yeah, it's fine.
So adding 5 blocks each time? Add 5 blocks each time?
Yeah.
Yeah.
Now on that one, is it easier to explain it, or is it easier to draw it?
What do you think?
Probably explain it that time, right? Make and test a conjecture. Number 9, that's sort of what we were just doing. You got product of 2 even integers. Give me 2 even integers.
2 and 4.
2 and 4. So we want the product. What is 2 times 4?
8.
Give me 2 more.
4 and 6.
4 and 6. What's 4 times 6?
24.
Anybody seen a pattern yet? What's always going to happen?
It goes up by 2 each time.
Answer's always going to be what?
Double.
Answer is always even. Answer is always even.